Here we're looking at example 8 from our 1.47 notes. We're asked for what value of k is this function pretty much going to be continuous. That's what we're looking for. We need to identify what k value will make him continuous. Well, if we just have our piecewise function, we notice that there's a little bit of a break here happening at -3. Let's go ahead and take our function, that 2x squared plus 5x minus 3 all over x squared minus 9, and just kind of look at him a little bit more closely, just because this k value could be literally anything. We have no idea what he is, but we can kind of maybe look and determine some things potentially with this other piece. Now, if we go ahead and factor this top, we end up with 2x minus 1 times x plus 3. Whereas on the bottom, we see that that is simply just the difference of two squares, and that'll factor out to be x plus 3 times x minus 3. Well, lo and behold, these x plus 3's can end up canceling, leaving us then with just 2x minus 1 over this x minus 3. Well, again, the bottoms can never be equal to 0. So as a result, let's go ahead and set this not equal to 0. We end up then with x minus 3 is not equal to 0. So we're seeing a vertical asymptote at 3. However, we don't really care what's going on at 3. We care about what's going on specifically at -3. So from earlier, we saw that they did cancel. Let's see then what's going on at -3. Well, we end up with x plus 3 is not equal to 0 as well. When you subtract that over, x is not equal to -3. This again is creating that hole. All right, now things get a little tricky. We have our simplified version. It's 2x minus 1 over x minus 3. That was, again, our simplified version coming from right here. Now, if you think about it, this is some y value. This top is considered to be some y value. Likewise, with that, you could actually take the limit of this entire top piece, figure out what it is, or, since it, again, this 2x minus 1 divided by x minus 3 is just a derivation from our original, we can actually then just say that this is the new y is equal to, or apply, same thing, that limit to it. Now, the reason why we want to instead just take the limit is because we're looking and seeing what is the limit as it's happening at specifically this x value -3. So that's really what we care about, the limit as x is approaching -3 of our simplified function. Now again, we're looking for this k value, and we have no idea what he is, but he is equal to some y value. Now it's our hope that this y value comes out to be the exact same thing as the limit as x approaches -3 of our simplified version of the function. So this would again equal some limit, and we want this to become k. And as a result of that, we can then say the limit as x approaches -3 of 2x minus 1 all over x minus 3 is equal to k. Since y is just equal to k, we can just bypass the whole y and go through and just say it's equal to k. Now when you go ahead and throw in -3 into the function, you end up with -6 minus 1 is -7 over -3 minus 3 is -6. So it looks like our k value just simply comes out to be 7/6. So k, in order for this to be continuous, specifically at -3, k would have to be equal to 7/6. All right. Now again, we couldn't just, it's not like you could just have x is equal to -3 over here. We actually had to apply the limit because we're looking and seeing the left side as well as the right side. What's the limit as it's approaching that? Okay, you couldn't just be like, notation-wise at least, x is equal to -3. They're close to the same, but they are very slightly different. Again, we've talked about how they're different in the past, but we had to apply the limit as x approached -3. And it was that goal that they ended up coming out to then be this k value equaling that y value. or that limit. Now, pretty much what I wanted to go ahead and do, k had to become 7/6 for that to be continuous. I wanted to go ahead and kind of show this graphically and show you exactly what's going on here. So if we go ahead and go to our graph, hit y equals, on our top function we have 2x squared plus 5x minus 3 divided by x squared minus 9. Close parentheses. So just graphing this thing, we see this type of function. Now, obviously we still have that vertical asymptote happening at +3, but at -3 there should be a little hole here. Unfortunately, we can't quite see that, but let's go ahead and go into our table. So we're going to go ahead and hit second table set. We're going to start our values at -4. We'll just start there and go by ones. And there you can in fact see that hole happening at -3. Now if we wanted to get a little bit closer, or actually you can kind of see that it's between 1 and 1.286. And in our calculator, if we just went ahead and hit second, quit, 7 divided by 6 is what we ended up with. We notice that that is in between those two y values that we just looked at. All right. So as you get closer and closer and closer, oops, we just want the graph. As you get closer and closer to -3, we saw that top piecewise function. So pretty much this entire blue actually represents the true top of that piecewise function. And then we have this other k value that we were looking for, here he is, happening at 7/6. So that takes care of that hole at -3. So on our graph, what would happen is you'd have like this little dot here that would fill in that value. Again, because it's just a y value, 7/6, specifically at that x value, -3. So it would actually be a point here, and thus making it continuous at -3. All right, so again, though, that is really what you're finding. You're finding that k value that would work and make this guy continuous at -3. We don't really care too much about what's going on at +3, just the -3 guy. All right. So again, though, that is example 8 from our 1.4 set of notes.